Welcome back to Talk Tensors. You know, we love to take a deep dive into the latest AI research, and today we're really excited to be digging into a paper called Boosting MCTS with Free Energy Minimization. This one really caught our eye, I gotta say.
Oh yeah, for sure.
Because it's tackling a really challenging problem, how to make AI systems that are not just good at planning, achieving goals, but also actively seek out new information to improve their understanding of the world.
Yeah, it's like giving AI a sense of curiosity,
right?
The drive to explore,
curiosity, exactly.
And learn, even when there's no immediate reward,
It's like intrinsic motivation.
Yeah, exactly.
Okay, so this paper focuses on Monte Carlo Tree Search, or MCTS. Can you remind our listener about what MCTS is and why it's so important?
Absolutely. MCTS is this really clever search algorithm that's been incredibly successful in game-playing AIs, famously in AlphaGo.
Right.
It's all about exploring possible future states and figuring out the best actions to take based on those simulated outcomes.
So like in a game of chess, it would be like looking ahead at all the possible moves.
Right.
And kind of trying to suss out which one is most likely to lead to a win.
Exactly.
Okay.
That's a great analogy. And what makes MCTS so powerful is that it can handle really complex situations where there are tons of possible actions and outcomes.
Right. Tons of branching possibilities.
Yeah, tons of branches.
Okay. So that's MCTS. But this paper takes things a step further by combining it with something called the free energy principle.
Right.
Now, I'll admit that one sounds a bit intimidating.
It's a mouthful.
Yeah, can you break it down for our listener?
Yeah, so think of free energy as a measure of how confused the AI is.
Okay.
It's constantly trying to minimize that confusion, either by learning more about the world or by changing the world to match its expectations.
I like that a lot.
Yeah.
So it's always striving to make sense of things, to find patterns, to make predictions.
Right.
And if something unexpected happens, it has to update its model of how the world works.
Yeah, exactly. And that's where the link to action comes in.
Right.
The AI isn't just passively observing the world. It's actively trying to shape it in a way that makes it more predictable, more in line with its understanding.
I see.
Yeah.
So it's not just about observing, it's about interacting.
Yeah, it's about interact.
And shaping.
Shape there.
Okay.
Yeah.
So in the context of this paper, they're using the free energy principle as a guide for how the AI should explore and interact with the environment.
Yeah.
It's not just about blindly trying things. It's about taking actions that will specifically reduce uncertainty and make the world more understandable.
Exactly. And that's where this idea of epistemic value comes in.
Oh.
The AI gets bonus points for taking actions that reveal new information, even if those actions don't immediately lead to a reward.
So like we're rewarding curiosity.
Rewarding curiosity.
I love it.
Yeah.
So instead of just focusing on achieving a specific goal, it's also driven to learn and understand the world around it.
Exactly. And this is a big deal because it means we can potentially build AI systems that are not just blindly following instructions, but are actually motivated to learn and explore on their own, just like humans are.
Right. So there's like an intrinsic motivation to explore.
An intrinsic motivation to explore.
Not just because we're giving it some kind of reward function that says, oh, you found the thing that you're supposed to find.
Yeah. It's like, yeah.
So cool.
Yeah.
Okay. So now we've got MCTS,
Right.
which is great at planning.
Yeah.
And the free energy principle, which is all about minimizing surprise and seeking out information.
Yeah.
How do they actually combine these two ideas in the paper?
They focus on a problem that's particularly tricky for traditional MCTS situations, where the AI has a continuous action space.
Okay.
Instead of just having a few discrete choices, it has an entire range of possible actions, like controlling a robot arm that can move in countless directions.
Oh, I see.
Yeah.
So like it's not just what to do, but it's how to do it.
Exactly. And that's where they introduced this really clever technique called the cross-entropy method, or CEM.
Okay, so walk us through that. How does CEM help with this continuous action problem?
So CEM acts like a smart filter, constantly refining the AI's focus towards actions that look most promising.
Okay.
It starts by sampling a bunch of candidate actions, evaluates them using short model-based rollouts, and then refines the action distribution based on the best performers.
I see.
It's an iterative process that keeps getting more and more precise.
So the AI is essentially learning from its mistakes,
Yeah.
like figuring out which actions are worth exploring further,
Right.
and which ones can be safely ignored.
That's exactly right. And the really clever part is that this refined action distribution doesn't just get used once it gets applied consistently throughout the entire MCTS process,
Right.
both for selecting actions and simulating outcomes.
Wow, I see.
Yeah.
So it's like they're establishing a consistent strategy that guides the entire search process.
Precisely. But of course, there's always a trade-off.
Right.
As the search tree expands and explores states that are very different from the initial state, the action distribution that was optimized at the root might not be ideal anymore.
It's like using a map
Right.
that was perfect for navigating downtown,
Yeah,
but might not be as accurate once you get out into the suburbs.
exactly. And that's an important consideration for anyone thinking about using this approach in their own work.
Right. There's always trade-offs.
Always trade-offs.
Okay, so we've laid the groundwork.
Mhm.
We understand MCTS.
Right.
We understand the free energy principle,
Mm-hmm.
the continuous action space challenge, and how CEM helps address it.
Right.
But how does this all actually perform in practice?
That's what we'll dive into next.
Okay.
The experiments and results that really show the power of this combined approach.
I'm excited to hear about that.
Welcome back to Talk Tensors. We're continuing our deep dive into boosting MCTS with free energy minimization. We left off talking about the theory behind it all, and now it's time to see how well it performs, when put to the test.
I'm definitely ready for that. What kinds of experiments did they run to evaluate this approach?
They tested it in several different environments, actually.
Yeah.
Each one designed to highlight, different challenges.
I see.
There was the classic pendulum problem,
Okay.
the deceptively tricky sparse mountain car, and then a couple of half-cheetah tasks
Wow, cool.
involving running and flipping.
So a pretty diverse set of environments to
Yeah.
test.
Yeah, quite a range.
Okay.
I'm particularly intrigued by the sparse mountain car myself.
Oh, yeah, that's a good one.
It's known for being tough because rewards are only given when the agent reaches a specific goal,
Right. It's like you don't get any feedback until you've achieved the thing.
Exactly. So it has to explore a lot
Okay.
to find that reward.
Makes sense.
So what did they find there?
Yeah, what happened?
The sparse mountain car results were particularly fascinating.
Okay.
Even though the MCTS CEM approach might be slower initially, it ultimately outperformed other methods, especially in later episodes.
So it's like it takes a little bit more time to get up and running.
Yeah, it's a slow and steady learner.
But once it's like
But once it gets going, it takes off.
it's unstoppable.
Yeah.
Why do you think it excelled in this particular environment?
I think the key is that it's so focused on exploration and information gathering.
Yeah.
In the sparse mountain car, you can't just stumble upon the solution.
Right.
You need to systematically explore the environment and learn how it works.
Yeah.
And the MCTS CEM approach is really perfectly suited for that.
I see. It makes a lot of sense.
Yeah.
It's a reminder that sometimes you have to slow down to speed up.
Yeah, exactly.
It's not always about rushing towards the goal, but about taking the time to learn and understand the environment.
Precisely. And they saw some pretty impressive results in the half-cheetah run environment as well,
Okay.
where the goal is to run as fast as possible.
Right.
Again, MCTS CM generally outperformed the other methods.
It's not just about exploration. It's about using that information to achieve a specific goal.
Yeah, exactly.
That's fun.
What about the half-cheetah flip task? Was it as successful there? What do you think?
Yeah, what happened there?
That's where things got a little more nuanced.
Yeah.
While MCTS-CM did okay in the half-cheetah flip environment, its advantage wasn't as pronounced.
Interesting. Why do you think that is? Was it just like not as good at flipping?
That's a good question.
Or was there something else going on?
I think it has more to do with the complexity of the task itself, actually.
Okay.
Flipping, compared to running, is a relatively simpler task.
Okay.
It doesn't require as much intricate planning or exploration,
Yeah, I see.
So the extra computational power of MCTS-CM might not have been as necessary in that case.
So simpler task.
Yeah.
Less need for all the bells and whistles.
Yeah, it's a reminder that the complexity of the problem really influences how much benefit you get from this more sophisticated approach.
Right. So matching the tool
Yeah.
to the job.
Exactly.
Okay, cool. Overall, it sounds like these results are really promising.
They are promising. Yeah.
Would you say this paper represents a significant step forward
I think so.
in AI research?
I think this research is incredibly exciting.
Yeah.
It gives us a new way to think about how to build AI systems that are not just good at solving problems, but are also good at learning, adapting, and exploring.
Yeah.
It's a step towards creating AI that's more curious, more flexible, and ultimately more capable.
That makes me wonder what other challenges this kind of approach could tackle.
Right.
I'm already picturing robots that can navigate unfamiliar environments,
Yeah,
learn from their mistakes,
exactly.
and even come up with creative solutions to unforeseen problems.
And that brings us perfectly to our novel nations section. This paper has sparked some intriguing thoughts about how we might push the boundaries of AI even further.
All right, lay it on me.
Yeah.
What novel notions has this paper sparked for you?
Well, one thought that keeps coming back to me is this. What if we could use this framework to create AI systems that are not just good at solving problems, but actually good at defining problems in the first place?
Whoa, okay, hold on. Define problems. You mean like instead of us giving the AI a specific goal, like win this game or navigate to this location, we're saying,
Yeah.
here's the world, go figure out what's interesting.
Exactly. Imagine an AI that could look at a complex system, like a city's traffic flow or a company's supply chain, and identify the bottlenecks, the inefficiencies, the areas where optimization could have the biggest impact.
That's wild. So it's like we're given a set of tools and saying,
Yeah.
okay, go figure out what needs fixing.
And not only fixing, but redefining what fixing even means.
Oh, well, okay.
What if the AI discovers that the problem isn't just optimizing traffic flow, but rethinking the entire transportation infrastructure? Or that the real problem in the supply chain isn't speed, but resilience to disruption?
Okay, so that's a whole other level. I mean, how could we even begin to implement something like that? That's such a mind-bending concept.
Yeah, it's a big one, but I think this is where the free energy principle really shines, you know?
Okay.
Remember, it's all about minimizing surprise, reducing the discrepancy between an agent's internal model and the world it observes.
Right. So the AI is trying to make sense of things, find patterns, make predictions,
Right.
and if it's wrong,
Yeah, and if its predictions don't match reality, that creates that surprise or free energy.
right.
Now imagine we give the AI access to vast amounts of data about a complex system
Okay.
and equip it with powerful learning algorithms that allow it to build a sophisticated internal model of how that system works.
So it's almost like we're giving it a simulator in a way.
It's like giving it a
Yeah,
simulator.
and letting it kind of play around with all the different variables. And through that play, it starts to really understand the system.
Exactly. And here's where the MCTS comes in.
Okay.
Instead of searching for a solution to a predefined problem, the AI could use MCTS to explore the space of possible problem definitions.
Whoa, my brain is like short-circuiting a little bit here.
Oh, yeah, it's a lot.
So the AI would be using MCTS to search for like the most interesting problems to solve.
Yeah, the most interesting
The problems that would teach it the most about the system.
The problems that would lead to the biggest reduction in free energy. Yeah, the biggest improvement in its understanding of the system.
That's really cool. So we're not just talking about AI systems that can solve problems, but AI systems that can help us understand complex systems in a whole new way.
Exactly.
It's like having a research assistant
Yes.
that can point us in the right direction.
That can tell us what questions to even ask.
Right. Oh my gosh. And then just think about the potential applications.
Oh, yeah.
I mean, imagine having this kind of AI working with like city planners or policymakers, business leaders.
Absolutely.
It's definitely a novel notion, but I really do think it has the potential to be super groundbreaking.
It really does.
Of course, we're still in the realm of what if, but that's what's so exciting.
That's what makes it fun.
It's these kinds of questions that really push the boundaries of what's possible.
Absolutely. And that's what makes this field so captivating.
Yeah.
It's about constantly pushing the boundaries, exploring new ideas, and seeing where they lead us. Who knows, maybe someday we'll look back at this paper and see it as the seed that sparked a whole new era of AI problem solving.
Well said. And on that note, we'll wrap up our deep dive into boosting MCTS with free energy minimization. A huge thank you to all of our listeners for joining us on this intellectual adventure. Be sure to check out the paper yourself. We've got the link in the show notes. And let us know what novel notions it sparks for you. We'll see you next time. Keep those tensors talking.